All right, morning. Got 8:30. Happy Thursday. Hope everybody's doing well. Couple warm-up things for you to think about this morning. So I have a set A and I have a set B, and I have a function from A to B, and I want to know what information do I get about the sizes of A and B if I know certain things about F. So if I have some things over here, and F's mapping everything from here into here. Remember, injection, same as one-to-one. What do I learn about the sizes of A and the sizes of B? How many elements can I fit into A versus B? Yeah, right. If I can fit everything from A into B one-to-one, if I can line up my elements with the elements in B, it's possible that B has extra elements that nothing maps to. But if everything in A has its own element in B that I can map to, then there must be at least as many things in B as there are in A. Must be the case that there are more things, or at least as many things in B as there are in A. What about if I have a surjection? So now I have another value in A, maybe, that points to the same thing in B, but I can definitely make every element in B. Any element in B is mapped to by something in A, by F. Then what do I know? Everybody's brains a chance to fire up this morning. So every element in B has at least one thing in A that gets sent to it. What do I know about how many things there are in B compared to A? Yeah, good. If everything in B has something in A, at least one thing in A associated to it, then there must be at least as many things in A as there are over here in B. Because for any element of B, I can pick one in A. I pick a different one in A. Because remember, to be a function, every element in A gets sent to exactly one thing in B. So we had this picture from last time. There was this trick question where I drew this picture. We tried to figure out if that was an injection, a surjection, or a bijection, and it was none of them because it wasn't a function. Right? It wasn't a function because this input had two outputs. Which is not allowed. So, if I'm going to be able to reach every value in B, that means I have to have at least as many values in A as I have in B. And so then what can we say about a bijection? Remember that a bijection is both an injection and a surjection. So that leaves the only possibility there's only a bijection if the two sets have equal size. So a bijection is really just a rearranging of the values, a renaming of everything in A to things in B in a nice one-to-one and onto correspondence. Everything in B has one thing in A, everything in A has one thing in B. All of that lines up nicely. Okay. So that's a good warm-up for what I want to start with today, which is if I have a set A that has m elements in it, and I have a set B that has n elements in it, how many different functions are there from A to B? How many different ways are there for me to draw these arrows? So I've got m things over here, n things over here, and I have to draw an arrow from everything in M, or from everything in A to something in B. How many different ways are there of doing it? M times n. Okay. Let's think about it. Let's think about how to approach a problem like this. Let's say this was a problem on your test on Monday, on test 4. How would we go about approaching something like this? Well, with two different variables, it's a little bit tough. So let's break this down a little bit. Let's think about what if m is equal to 1? What if I only have one element of A and I have n elements of B? So I have 1 over there, n over here. How many different ways are there of drawing an arrow from my one element over into B? Yeah, good, right? There's n different arrows I could draw. Here, here, all the way down to here. So n functions. Okay, so maybe if we're thinking about m times n, 1 times n, that's looking good so far. Let's also try another simple example. What if n is equal to 1? So now I have m things over here in A, and there's only one value over here in B. How many ways are there to draw one arrow from everything over here in A? So if I look at this first element, where's the arrow going to go? Okay, I got a couple of people saying M, but I'm not sure I believe that. Let's look at this first element. There's only one choice. It's got to go over here. There has to be an arrow, and it has to point to that. Second choice, has to be an arrow, it has to point to this. Last choice, has to be an arrow, has to point to this. Just one option. Is it blurry? It's not on my preview, but I don't know. Could be any number of things. I can maybe I've got it, I haven't zoomed it in. There we go. Apologies for that. Oh, now it's frozen. How are we doing? Okay, we're back. There we go. Little small before, but now I've zoomed it in. Okay, so if n equals 1, now we only have one function. There's only one way to do this. Everything has to point to the one element. So m times n not looking so good anymore, right? Because m times n we would expect m, but we only have one option. So let's expand on this case just a little bit. What if n equals 2? So I have a is over here. Still have my m different elements. But now over here in B, I have alpha and beta. So I have to draw an element. I have to draw an arrow from this first element. What are my options? This first arrow can go to alpha or it can go to beta, right? So I've got two choices. Over here, I just had one choice. But here I have two choices for the first element. How many choices for the second element? Also two. How many choices for each element? Always two. So if I want the total number of functions, I can do a rule of product calculation. Right? My process is choose whether the first element goes to alpha or beta. That's two options. Choose whether the second element goes to alpha or beta. Two more options. I've got m choices, each one of which has two options for a total of 2 to the m functions. Okay. So now let's go back to the original question. If a is m and b is n, how many functions do I have? I want to make sure my answer matches all of these cases. And I want to think about the lessons I learned from this case. How can I answer that question? M to the n, close, not quite right. That wouldn't match 2 to the m. N to the m, there we go. There are n to the m different functions from A to B. Why? Well, because I'm going to do a rule of product counting. I'm going to have m steps, and there's going to be n options at each step. My m steps are, what does each element in A go to? And my n options are whatever is in B. And now I should check. I should check my answer. Does that match all three of my small cases I did? If m equals 1, then this is n to the 1. That checks out. If n equals 1, 1 to any power gives me 1. That checks out. If n is 2, then I get 2 to the m. That's matching this formula. So I'm confident in my answer. Next question. As soon as we feel good about one, there's always another question. How many, not just functions from A to B, but how many bijections f from A to B are there? So first, what did we learn in the warm-up? What do we know has to be true in order for there to be any bijections? We still need A to be equal to B, or in this case, N to be equal to N. So we need N to be equal to M, or there are no bijections. Okay. So now let's do the same thing. Let's try some small cases. See if we can figure it out. So N equals M equals 1. Nice easy case. How many bijections are there? Just one. I drew it. There it is. You got one element and one element, and you got to send the one element to the one element. Great, we're done. That's nice and easy. One bijection. Okay, I don't see a pattern yet. Maybe it's clear to you, it's not clear to me. So what's our next case? That would be N equals M equals 2. Here's my A, here's my B. Okay. So if I look at this first element, how many options do I have? Where can I send it in B? Got to draw an arrow. It's got to come out of this dot. Yeah, right? I've got two different options. It can go anywhere. Let's pick here. Once I've picked where this first element is set, how many options do I have for this second element? If I say this one goes here and I want a bijection, then I only have one option next. So that's one bijection, drawn in orange. Here's another bijection, drawn in blue, where instead of picking the bottom one first, I pick the top one first, and then I only have one option left over. And those are my only two bijections. My first one can be top or bottom, and once I pick my first one, my second one is fixed. Maybe you can see a pattern, maybe not. Let's do one more. N equals M equals 3. How many options for my first arrow? Yeah, 3 options, right? I could go straight across, or I could go to the middle, or I could go to the bottom. So 3 options for the first one. Once I've picked my first one, how many options for the second arrow? Now I've got 2 options, right? This one, the orange bijection, I can't go to the I can't have 2 orange arrows going to the same place, but I still have 2 options. I could go there, or I could go down to the bottom. If I have a blue bijection, then I just can't go to the middle, but I could go back up to the top, or I could go to the bottom. And for the red one, I just can't go to the bottom, but I could go to the top or across to the middle. Starting to become a very busy picture. So 3 options for the first one, 2 options for the second one. How many options for my last element? Only 1 option, right? It's whatever is left over. So in the orange bijection, I have to go straight across. In the blue bijection, I also have to go straight across. And in the red bijection, it looks like I got to go up to the middle. And I've drawn 3 of them, but I skipped out on some. What I had was 3 options for the first one, 2 for the second one, and 1 for the third one, giving me a total of 6 bijections. So what do we think about the general case? What about n equals m? How did we get 6? Where did I get 6 from? Well, I had 3 options for my first vertex, top, middle, or bottom. And then given my first vertex, I had 2 options for my second vertex. It couldn't be the same one as the first one, but I had 2 other ones going on. And then 1 option for the last one. It had to be what's left. Yeah, so I need n equals m. In the general case, it's looking like m factorial, which is n factorial. Whichever one you like best. So we need n equals m, otherwise there's none. But if n is equal to m, then factorial is... And we can see, right, what's the rule of product calculation? It's, I have m choices for the first, it can go anywhere, and then I just can't repeat. So m minus 1, and then I can't repeat either of those, so m minus 2, all the way down to 1. Okay, so next question maybe shouldn't be a surprise. How about how many injective functions? Question. Somebody raised their hand. I didn't see who it was, but... Well, if you have a question, feel free to type it or ask it, but I'm gonna keep going. Okay, so how many injective functions? So what do we need there to be? What did our warm-up tell us? When can there be injective functions? What condition on n and m has to be true? Injective functions, I need to fit A inside of B. So I actually need A to be smaller than B, and I think we said I have N and M maybe backwards here, but A is M, B is N. So I want M to be smaller than N. So I'll write this like this. The size of A, which is equal to M, has to be smaller than N, which is the size of B, in order to fit. So let's do some small cases, see if we can work it out. Let's say m equals 1. Right, that's our nice easy case. And n just has to be bigger than 1 or equal to. Here's my A, here's my B. How many functions are there? How many options for this one arrow? n choices over here. Yeah, all right, I've got n different places I can send this one arrow. I could send it to the top function, to the top value, that's one function. I could send it to the second one, that's a different function. Right? This is f of a equals 1. This is f of a equals 2. Those are different functions. All the way up to that one, giving me n different options. So, this would be n injections. So let's try another case. Let's try m equals 2. Make it a little bit harder. See if we can figure out general pattern. Keep drawing my pictures. And over here. So how many options for the first arrow coming out of this element? Yep, still n. Still can send it anywhere over here. And now, once I've picked my first element, how many ways are there for my second element? So if I just wanted any function at all, it would be n again, and I would have n squared functions. But I need this to be an injection. I need it to be 1-to-1. That means you can't pick the same value. So how many options are there for this second value? n minus 1. I just have to pick something different. In order to be an injection, I create this process. It's very much like the bijection, except I only have to pick for every element in A. So how many, so this is n times n minus 1 injections. So in the general case, I start by picking my first vertex, there's n options, and then in my second vertex, there's n minus 1, and I keep going, I keep picking, but I don't go all the way down to 1. Well, I would if m was equal to n, because that's a bijection. We know that already. But I get to stop when I run out of elements in A. So where is it that I'm going to stop? What is my last value? Here I have one element. My last value is n minus 0. Here I have two elements. My last thing I multiply by is n minus 1. So I don't keep going all the way down to m, because here that would mean I keep going all the way down to 1. Right, I need m total terms. Really good. M total terms. So what is the last term? It's got to be related to m somehow, but I don't go all the way down to m. N minus m is close. M plus 1, m minus 1. N minus m doesn't quite work though, right? Because when I had 1 here, I stopped at n. My last term was n minus 0. When I had 2 terms, my last term was n minus 1. So n minus m isn't quite right. Still looking for the answer in chat. What matches that pattern? I want n length of m minus 1. Yeah, I want m minus m plus 1. That's what matches my pattern. So this will have m total elements. I'm counting minus 0, minus 1, minus 2, all the way up to minus m minus 1. That gives me m total things. The other way to see that is, if I have one thing, I stop at 0. If I have two things, I stop at 1. If I have m things, I stop at m minus 1. So this is also n minus m minus 1 in parentheses. Is another way to see that. And I have a really nice way of writing this. It looks like n factorial, but I don't keep going. I'm canceling out everything from n minus m on downwards. So I'm dividing by, sorry, not m factorial, n minus m factorial. This leaves me with n times n minus 1 times n minus 2, all the way up to n minus m plus 1, and everything else gets canceled out. Yes, exactly. I'm counting a permutation. I want to permute m. I want to choose a permutation or a permutation of m of these elements to match up with a. Does this count having the other elements not map to anything in B? So remember, we can't have anything. There's nothing in A that maps to nothing in B. It's not possible to have something in A that maps to nothing in B, because that's not a function. We require functions to have exactly one output. So I have to send everything to somewhere in B. Can't be sent to nothing. But it's a good question, a good thing to keep in mind. Okay. So we counted functions, we counted bijections, we counted injections. What's the next question I'm going to ask? Total functions, bijections, surjections, injections. It's got to be surjection next, right? Next natural question to ask would be, what about surjections? And it turns out that surjections are a lot harder. How many surjections? How many onto functions from A to B? Okay, well, there's one thing we can say for sure. What condition do we need on m and n? In order for there to be any surjections. Yeah, I need m to be at least as big as n. In order for me to map to everything in B, I have to have at least one thing in A for everything in B. And we could try doing the same thing. In fact, let's do that. Let's try doing some of the small cases like we did before. So let's try n equals 1. Okay, so I've got m things over here in A, and I only have one option for B. How many surjections do I have? Where does this first arrow go? just one option, right? First arrow, there's only one choice. It has to go there. And second arrow, still only one choice. Still has to go here. And every arrow has to point to exactly here. So if n equals 1, not so bad. Just one surjection. But already, if I make n equals 2, things get a little complicated. Here's A. Here's B. Got two things going on over here. And I got m elements over here to choose from. How many options for my first arrow? Two choices, right? It can go to alpha or beta. No problem there. But how many options for my second arrow? It's not one option, right? It's still two. I can still go to either place. It's really not until my last arrow that I run into trouble. How many options for my last arrow? It depends. If anything has pointed, if both of these already have an arrow pointing to them, so if anything between the second and the last has pointed to something other than the first, then I have two choices for the last arrow. But if I always chose the first element, then this last arrow has to point at B. And this is why surjections are hard. Surjections are hard because the number, you can't really write it out like a rule of product. Because the number of options for this last one depends on what you did previously. This is two options unless nothing else points to beta. Then it's only one option. And so we actually need a different way of thinking about this. And here's the way we're going to do it. Here's A. Here's all my elements over here. What I need to do is break A up into n different parts. And I need none of these parts can be empty. And then each part I'm going to send to a different element of B. And that's how I'm going to assure that I have a surjection. Because if each part is not empty and each part gets sent to a different element of B, then everything in B has at least one thing in A that gets mapped to it. And so maybe let's look at a specific example. Let's say that A is the numbers from 1 up to 7, and B is the numbers from 1 up to 3. What I need to do is split the numbers from 1 to 7 into 3 different groups. So I could do that like 1, 2, 3, 4, 5, and then 6, and then 7. Or I could do it like 1, 2, 3, 4, 5, 6, 7. Or I could do it like 1, 2, 5, 6, 7, 3, 4. All of these are different ways. In these two ways, I have one group of size 5 and two groups of size 1. In this example, I have two groups of size 2 and one group of size 3. And here, even though the group sizes are the same, the individual groups are different. So all of this is going on, and then on top of that, even with this one group, I have different surjections. I can send all of this group to 1, I could send all of this group to 2, and then I could send all of this group to 3. So here's my rule of product calculation, my rule of product process. Step 1 is going to be break the m elements of A into n non-empty pieces. And there's going to be a big question mark here. How many ways to do this? I don't know. That's going to be a separate question. And then I'll come back to that question. My second step is pick a different value of B for each part of A. And this at least I know how to do. I have n parts and n elements of B. How do I pick a different part of B, a different element of B for each part of A? So over here, I have n parts. And over here, I have n elements. How many ways can I match those up? Sorry, I'm a little off the bottom here. How many ways are there to do step 2? Not quite n choose n. I want n factorial, right? Because order does matter. I have n options for this first part, n minus 1 options for the second part, n minus 2 for the third part, and so on. Each part gets sent to a different value. What I've basically done is I'm choosing a bijection between the parts and the elements. Yeah, I'm going to talk more about the partitioning in a second. This is n factorial ways. So the second part, once I have my parts, once I've broken up A into n different parts, then I have n parts, n elements. I just need a bijection from parts to elements. That will assure that I have a surjection, because everything in B, the part that gets sent to B is not empty. So there's at least one thing in each part. That one thing is what gives me a surjection. The question is, how do I build these parts? How do I break A up? Break A up into n non-empty parts. And so this is called a partition of A. If A is a set, a partition of A is a collection of subsets let's call them I1 all the way up through IN, such that if I take the union of all the subsets, I get A back. So this means every element of A is in at least one of the subsets. And then I also want I sub I intersect I sub j to be equal to the empty set if I is not equal to j. This means no element of A is in two different subsets. So this is exactly what I'm talking about when I talk about breaking up A into non-empty parts. I want a partition. I want each element of A to show up exactly once in one of my different parts, one of my n parts. And so the question we need to answer is, how many ways are there of doing this? And the answer is complicated enough that it has its own special function and name. These are called Stirling numbers of the second kind. Let me write them S, M, N. So S, M, N is the number of ways, number of partitions of a set of M elements into N parts. Now, if you keep taking math courses, in particular if you take Combinatorics 1, I don't remember the course number for Combinatorics 1, we can learn a formula for Stirling numbers of the second kind. Here's the formula. Ends up looking like that. But you don't have to know this formula. All we are worried about is S of M comma N. And our number of surjections using our rule of product from before is S of M comma N times N factorial. So first we break our set A, which has M elements, up into a partition with N parts. S of M, N, Stirling number of the second kind, number of ways to do that partitioning. And then we create a bijection between our parts and our elements of B in N factorial ways. And that's our number of surjections. Okay, let's go ahead and take our break there. That was a bunch. We'll come back in 2 minutes at 9:23. We'll start back up again. Go grab some water, grab a snack, think about what questions you might have, and we'll gather back together. Okay, let's gather back together. Hopefully had a second to let that sink in. So a couple of quick comprehensive questions. What is S of m comma 1? And what is S of m comma n? So m comma n, I want to break a set of m elements up into n parts. How many ways are there to break m elements into one part? Just one way. Good. The only way to break m elements up into one part is to just have them. That's your one part. How many ways are there to break m elements up into m parts? Not quite m. So let's think about it. If I have 1, 2, 3, all the way up to m, and I want to split this into m different groups, how many things are going to be in each group? So if I want to split this up into one group, my one group would be everything's all together. If I want to do m groups, how many elements are in each group? Just one element per group. Good. So how many ways are there to draw m circles around m elements? Well, I draw a circle here, I draw a circle here, I draw a circle here, I draw a circle here. Is there any other way to draw the circles? There's only one way to draw these circles. SMM also one. Only one way to break m things up into m sets is to put each thing in its own set. One more, just for fun. What is S of m minus 1? So I have my numbers 1 through n. And now I need to draw m minus 1 circles. So maybe I draw a circle around 1 and 2, and everybody else gets their own circle. Or maybe I draw a circle around 7 and 4, and everybody else gets their own circle. How many different ways are there to draw m minus 1 circles around m elements? Not quite 2, right? Because I could do 1 and 2, I could do 1 and 3, I could do 1 and 4, 1 and 5, all the way up to 1 and m. Or 2 and 3, 2 and 4, 2 and 5, all the way up to 2 and m. But you've got the right idea. Where does the circle with 2 elements go? How many ways are there to pick 2 elements to be in that special circle? Yeah, there we go. M choose 2. M choose 2. I pick 2 special elements to be in the circle with 2 things. Everybody else gets their own circle. M choose 2 ways there. So these Stirling numbers of the second kind, they're complicated. And since they're complicated, the number of surjections is much more complicated. Okay, let's move on. More stuff to talk about. Got to make sure you're ready for the quiz and ready for test 4. So, something a little bit more familiar. F goes from the real numbers to the real numbers. F of x is equal to the square root of x. Is this a function? Depends on the domain. Well, I told you what the domain was. Domain is all real numbers. Yeah, right? Not a function. It's not a function because f of negative 1 is undefined. Okay. How about f from the non-negative real numbers to the real numbers? Or let me call it g, actually. It's a better name. G of x is square root of x. Is g a function? Yeah, right? No problems here. You can always take the square root of a real number and get a real number. Okay. So here's the question. What if I really wanted a function that was from real numbers to real numbers and worked kind of like the square root function? Right? This is g of x. I know what it looks like. And I know f of x isn't a function, but what if I wanted to make a function that agreed with g of x, but I was allowed to plug in any real number? I want a function like g of x, but where any real number can be an input. So, I mean, you can think of some. It's not too hard to imagine one. Yeah, right? Square root of absolute value of x. Now, h is a function from reals to reals, and h does its own thing on the negative numbers, but then h and g line up perfectly. There's no way to really draw it with the two colors, but they line up perfectly on the g of x part. And that's not the only option. I could also do, try and get another color involved here. I is a bad name for a function. Let's call it L of x. I'm going to make it square root of x if x is greater than or equal to 0. And I'm just going to make it 0 if x is negative. Right? This is another function, does its own thing on the negative numbers, but then matches g perfectly where it's defined. And so we call functions like h and l extensions of g. And the idea is, if we only use the part of the domain, here L is also from reals to reals, if we only use the part of the domain where g is defined, then they would be equal. So first we're going to talk about restriction, and then we're going to talk about extension. The definition of restriction. So let me first say, let A1 be a subset of B. No. Try that one again. Different color. Green was cursed. Let A1 be a subset of A, and f be a function from A to B. The restriction of f to A1, which we write f restricted to A1, is a function g that goes from A1 to B with g of A always equal to f of A. So I can restrict something like, let's do f of x is x squared, and its domain is all reals to all reals. But A1 is the set -1, 0, and 1. Then f restricted to A1 is a function where the only inputs allowed are -1, 0, and 1. So this is a function that takes -1, 0, and 1 and spits out any real number. So the range of f is all non-negative numbers, right? You can get any number. If you take a real number, you can square it, you can get any non-negative number. But here the range is only 0 or 1. I'm only allowed to input -1, 0, or 1. So this is a restriction. Underline my word I'm defining. And then an extension is the opposite of a restriction. So I'll continue my definition. If, so again, let A1 be a subset of A, and now I'm going to let G be a function from A1 to B, then F is an extension of G if F restricted to A1 is equal to G. So if when I restrict F to the smaller set, I get G, then F is an extension of G. Okay. And all of this, I'm cheating a little bit because I'm saying that two functions are equal, and I haven't really said what it means for two functions to be equal. So let's ask that question now. When are two functions equal? So two things need to be true. They need to have the same domain. This function and this function are not equal. Right? Think about the graphs for each one of these. This one I'm allowed to input any real number. This one I'm only allowed to input positive numbers or non-negative numbers. They don't have the same graph, so they're not the same function. Good. So first they need to have the same domain, and then, exactly as was mentioned in chat, the same input should give the same output. So when are two functions equal, they need to have the same domain and f of x has to be equal to g of x for every x in the domain. Okay. So, question, if f of x is equal to x and g of x is equal to x cubed, and these are both functions from the set -1, 0, 1 into the reals, is f of x equal to g of x? Yeah. Even though I've written them differently, even though I wrote this as f of x and this one as x cubed, f of x is equal to g of x. They are the same function. They all turn minus 1 into 1, 0 into 0, and 1 into 1. So the equation doesn't matter for a function. All that matters for a function is the rule. And the rule is how inputs get turned into outputs. So if the rule is minus 1 goes to minus 1, 0 goes to 0, 1 goes to 1, then these two functions are the same, no matter how I've written them. Okay, one last topic I want to talk about today. I only have a couple of minutes, so I can't do the nice connection thing that I like to do, but we'll talk about this more on Tuesday, are the ceiling and floor functions. So the ceiling function looks like this. And this is the ceiling. And the floor function looks like this. And the way these functions work, they're both from real numbers to real numbers. And actually, they're from real numbers to integers. And these functions want to find a way to turn real numbers into integers. And this is something that I think you've probably come across before at some point. But the idea is for a ceiling function, the intuition is rounding up. And for a floor function, the intuition is rounding down. But we want to be a little bit more precise than that. Because negative numbers can sort of mess with that, right? What is rounding up and what is rounding down when you're dealing with negative numbers. So instead, we're going to define these a little bit more precisely. So I want to define the ceiling function to be the smallest integer that is greater than or equal to x. And the floor function is the opposite. That's the greatest integer that is less than or equal to x. Okay. So let me do some quick examples. What is the ceiling of 7? What is the smallest integer that's greater than or equal to 7? Seven. Good. What is the ceiling of 7.0001? Now I got to go all the way up to 8. Right? The smallest integer that is bigger than 7.001 is 8. 7 isn't big enough. Got to go up to the next one. What is the ceiling of negative 1.1? There we go. Lots of answers. I want the smallest number that's bigger than minus 1.1. So I look at my number line, and I have -2, -1, 0, 1, and I find -1.1. It's right here. And I look for the first integer that's bigger than it, and that gives me -1. So this is equal to And we could do similar things for the floor function. So floor of 7, floor of 7.0001, floor of minus 1.1. Floor of 7 is still 7. 7 is an integer, so it's both the smallest integer that's greater than or equal to 7 and the biggest integer that's still smaller than 7. The floor of 7.0001 is still 7. 7, you can't find a bigger integer that's still smaller than 7, but 7 is smaller than this. And now the floor of minus 1.1, I find minus 1.1 on my interval. I look for the biggest thing that's still smaller than it, and this is minus 2. Okay, so that's ceiling and floor functions. I do want to talk more about what this have to do with functions, but I'm going to have to wait until Tuesday because that's the end of our time. Okay, quiz. What are we up to? 8, maybe, this weekend, and then test 4 on Monday. I have office hours later today. I have office hours on Monday before the test. So if you're worried about the test, please come talk to me. Let's do problems together. Let's talk about things. Also available for appointments if office hours don't work for you. But okay, I'll stop the recording here, and I'll see everybody at office hours or next week.